Right. So let's look at a couple of examples. Here we're comparing the pKa. We're comparing the pKa of this hydrogen. So let's look at what really this example is dealing with is basically comparing the two conjugate bases. So this is the conjugate base. If I remove this proton, I will have a pair of electrons here, negative charge. And then if I remove that OH proton, this is what the conjugate base looks like. That's negative. Put my double bonds in there. So what you're comparing here is how stable the conjugate base would be for either one of these. The conjugate base here is a lot more stable than this conjugate base, and for one reason, it's resonance, right? I can do resonance here and here. That's one resonance form, and then I can do multiple resonance forms for this structure, whereas here there's no resonance. All right, so because I can't do resonance with that top structure, then that means that the conjugate base that comes from deprotonation of the blue proton is much less stable. Here's another example, and what we're going to be comparing is this red proton here and these blue protons here on this amine, right? And again, in order to do the comparison, we need to look at the conjugate base for each one. So let's do this O, and all right. This is the conjugate base if I pull off the red proton, and then this is the conjugate base if I pull off one of the amine protons, NH, lone pair, negative charge. All right. So now what are we comparing? Are we comparing resonance? Let me put the electrons in here, right? You can do resonance here, and you can do resonance here, right? So the question is, what are we comparing? We can't really compare resonance because they can both do resonance. What we want to compare now is electronegativity, right? In this conjugate base here, the negative charge is on oxygen. In this conjugate base, the negative charge is on nitrogen. And so because oxygen is more electronegative than nitrogen, then this conjugate base is more stable, meaning that the red proton has a lower pKa. So this proton here is going to have a lower pKa and be more acidic. Okay, so what about this structure? Well, we're comparing this proton to this proton, and we're trying to figure out which one is going to be more acidic. So for that sulfonate proton, let me just draw this O minus, right? And then the amine proton that comes off, let me draw that. But this is nitrogen, and now it has two lone pairs, negative charge, and then S double bond O, OH. Right, again, what are we comparing? Here we have a negative charge on nitrogen. Here we have a negative charge on oxygen. They can both do resonance. But again, oxygen is more electronegative, and it has more resonance forms. You can push these electrons here, or I can take and I can push those there and push these here, or I can take this same pair of electrons and push them here, and then break this pi bond, right? So I can do two resonance forms here. Here I can only do one. With nitrogen, I can only do one resonance form, and that would be to go from here to here and then break the pi bond in the carbonyl. So this has more resonance, and oxygen is more electronegative. So when you compare the two, this proton here, the blue proton, is more acidic because of the fact that you can do multiple resonance forms, and the oxygen is more electronegative than nitrogen. So with this question, it's asking about the pKa's, asking which proton is going to be more acidic. Let's just take this example here, and let's compare HCl and HBr. If you compare those two, again, you have to compare the conjugate bases. For this, it would be Cl minus. For this, it would be Br minus. So now it's a question of size versus electronegativity. Chlorine is more electronegative, but bromine is larger. So that means the conjugate base is more stable. And because of that, HBr should be more acidic than HCl. And any of these you can verify by Googling the pKa of the specific acid. Right? Let's look over here, because this example E is comparing something that we haven't talked about yet. So let's draw this alcohol out. All right, so these are 2 carbons, and each carbon has 3 chlorines attached. And then here, that's chlorine, and then this is also chlorine. So you got to remember that chlorine is really electronegative. So there's a huge dipole moment pulling towards chlorine. And then if we make the conjugate base, which is we get rid of the proton by deprotonating it and make oxygen negative, that negative charge in the conjugate base is going to be stabilized by induction. Right? And because of that, this proton is going to be much more acidic than this proton, just simply because the chlorines provide that inductive effect and they pull electron density away from the oxygen in the conjugate base. So in this example, let's look real quick. It says write an equation for the proton transfer. That's simply the conjugate base picking up, or the base picking up a proton. So let's take that middle base, tert butoxide, and I'll draw the electrons in. So this is negative. If we put that in the presence of an acid or H+, it's very simple. It's the same mechanism. The base is going to give a pair of electrons to H+, and the base is going to get protonated to become the conjugate acid. In this question, it says write an equation for the proton transfer. So let's just take one of the acids. We'll take C. So this acid, right, oxygen has a positive charge. And then if I treat that with a base, let's just say hydroxide, that's negative, right? All this question is asking you to do is take a pair of electrons from the base and deprotonate the acid, right? And remember, it's the same set of arrows where you go from base to proton, and then from the bond between the proton and whatever is bonded to back to that atom, right? So this would be the conjugate base, and then this would be the conjugate acid.